Bob got his undergraduate degree at Allegheny College, and then went to University of Washington, did his master's and PhD in 1980. After that, went to University of Kansas in Lawrence. Spent a couple of years there, and then got out of Kansas and went to San Jose State, and has been there since 1984. And he's been all over the world, from the Himalayas to Oman, but most of his research has been concentrated in the Pacific Northwest and looking at the Cascades. He's very interested in what arcs look like deep underground. So he's in the internal structure of volcanic arcs is his main theme here. And today we're going to go back in time. We're going to go into the Eocene around 50 million years ago and look at some really interesting tectonics that happened on the Pacific Northwest. So with that, I definitely want to thank Bob Miller and introduce Dr. Miller. There you go.
Thanks for the very nice introduction, and it's pleasant. I haven't been in Chico in a long time. The train stops at like 3 in the morning. I've taken it a couple of times from Portland. I never really wanted to jump out at 3 in the morning to sit and check it out. So yeah, it's nice to be here. So as Todd said, I've been doing lots of different types of projects in the North Cascade range of Washington, and I thought I'd today talk about a topic that might be of more interest, but interest in terms of modern day California, in terms of thinking about what happens when ridges enter trenches and what the effects are, or when they come into contact with it. So what I'm going to do today is a summary of a lot of our work, group work, with some of, I think, 3 or 4 of my master's students, a couple of senior theses, colleague Stacia Gordon at Nevada Reno, and her students, and a long-term project of uranium lead dating with Sam Bowering and his, particularly his students at MIT. So anyway, this is a group effort. Please, if you have a question that seems if I'm not explaining something well or using jargon, don't hesitate to ask. I don't mind getting interrupted on that. And I've tried to put in some pretty pictures too, because I enjoy working in scenic areas like the Cascades. So with that, we're going to focus on the Eocene, and the title sort of explains it: ridges and ridge-trench interaction. So if we just think of plate tectonics, we have a lot of oceanic ridges, and oceanic ridges eventually make their way toward subduction zones in the continental margins. And they're going to interact at that continental margin, like what happened in California, starting in the Miocene and continuing to today, although California is a really messy situation. What I'm going to talk about is the Eocene, I think general consensus, at least of the broad tectonic outlines in the Eocene about 50 million years ago. But one of the things that makes the North Cascades an interesting place, and the Pacific Cascades as a whole, is that there are different crustal levels exposed because of exhumation, uplift of the mountain range. And so you can see the response to the effects of a ridge coming into a trench, both in shallow basins and active faults, or in faults like we have today here, and also we can see things that were maybe happening at 15 to 20 kilometers or even greater depths. So that's the pitch I'll make for why this is significant. So let's step back and look at probably the best example, though, on the planet today, and that is in South America, where there's a triple junction, the Chile triple junction. It's down in Patagonia, and the ridge has come in. It's because the ridge is offset by transform faults, by fracture zones. It's been coming in at different times. This triple junction is migrated, and here shows some of the effects you might see. Notice this is the Andean arc, the southern Andean arc, and there's a big gap right here. And that's where the actual ridge is interacting. So the subduction zone essentially has been shut off in terms of producing arc magmas. There's a whole series of volcanics, mafic volcanic rocks, basalts, in the back arc, and you can track them. They nicely agree time-wise, or more or less, going with the age of when the ridge collided or when it was subducted. There's a fold and thrust belt that seems to initiate it as well, with that and restricted to where the Chilean ridge is coming. So we can think of that as one example. We can go to this diagram. It goes way back to it's a modification of Dickinson and Snyder for California, the idea of a slab window. Again, where a ridge comes in, you no longer have the spreading, at least the formation of the ocean ridge. So here again would be our ridge coming in. We still have subduction if we have to the left and to the right, but we have this gap in the middle. Hottest asthenosphere rises up, melts, gives us weird volcanism. There's a change where strike-slip is initiated commonly in this situation. And again, we may get very anomalous magmatism. If you don't know all these names, don't worry about it. The point is there are volcanic rocks that are getting erupted in the forearc. So this is a hallmark of ridge trench interaction. Forearcs towards a subduction zone or Great Valley like here should be really cold crust, geothermal gradient, but yet we're getting volcanism or even in some cases plutonism and low pressure, medium to high temperature metamorphism. Again, very anomalous, shouldn't be happening in an area where we might think of Volusius forming, say in the Franciscan in our case. All right, so with that in mind, this is one rendition at 50 million years. It's colorful, so I use this one first. But this is the rendition here is there's a Farallon plate. There's controversy whether there was a plate that's now totally gone called the Resurrection plate. The Kula plate, everyone, that's an old name. Again, a plate which has essentially disappeared in the northeast Pacific. And it doesn't matter to us so much for what we're talking about, but the important thing is there's a ridge coming in to the subduction zone and either a window or we'll talk about the slab, whether it's truly forming a big gap or whether the slab is just breaking off intact and then going down and leaving an area with anomalous mantle or deep mantle rising up. So weird things happen, to make it simple for not weird, but we're going to be changing the plate configuration at that time. Okay? All right, so here's a diagram from one of our recent papers, just showing one other big complication that is generally agreed upon, and that is we have a ridge. So this is, now we're calling it the Kula Farallon. This is the other interpretation. But an important part of this scenario is there is a large igneous province in the Pacific Northwest called Siletzia. And Siletzia, or the Siletz volcanics in Oregon, Crescent volcanics in the Olympic Peninsula of Washington, there's lots of evidence from the chemistry, and I don't have time to go into that, that again this would fit with some sort of perhaps oceanic plateau. But the analogy that's been drawn, and I think is a good one, is this may be much like Iceland today, where there was in proximity to a ridge, there's a hot spot, and as you're probably aware, Iceland is very thick crust, oceanic crust, very broad. And so try and envision what would happen, or will happen probably, when Iceland enters a trench or tries to be subducted in the trench. So this is a complication that we don't have in Chile or in California in the same sense, at least not in the Neogene in California. So this is a big factor. There appears to be a change, we'll argue, for strike-slip. And I also should point out that we go up into northern Alaska, or southern Alaska, excuse me, but to the north, there's something called the Yakutat Terrane, which is colliding with the continental margin there that may be responsible in part for the really high elevations in Canada and the US, where it's over 19,000 feet, right where it goes around here in the bend. And so anyway, this is apparently a piece of this Icelandic-like Siletzia that's been sliced off to the north. Okay, so I just wanted to get you thinking about that, what likely was the scenario. Here now to get down to more looking at geology on a regional scale and more detailed. This is where the Siletzia lies. So here's the California border. It makes up generally kind of rainforest terrain of western Oregon, as I said, up into Vancouver Island. We have the modern, what I consider modern Cascade Range, which starts at around 42, 43 million years, the north-south Cascade Range. And then the North Cascade Range, which is about the latitude of Seattle northwards in the mountain range. And you notice there's a lot of faults that trend northwest. Just as the Sierra Nevada had more of a northwest-southeast trend in the Mesozoic, the same thing applies for the North Cascades before the modern Cascade Range came in. There are metamorphic core complexes to the east, which are also Eocene. These are the ones in Washington and in Idaho. But the largest metamorphic core complex, if you're familiar with that concept, the largest known one in the Cordillera in western North America is called the Shuswap complex in southern British Columbia. So these were all Eocene, these were active in Eocene, essentially the same time as frame that I'll be talking about. Okay, so these are the big tectonic elements we might think about. Now let's go in and actually look at the North Cascades. So if we look at the Cascades from at least up until about 60 million years ago, and maybe earlier or later, it was part of the largest Mesozoic batholith and early Cenozoic batholith in North America. It's actually about 3 or 4 times the volume of the Sierra Nevada batholith, going from Yukon and southeast Alaska all the way down into northern Washington, okay, called the Coast Range batholith. In Washington state, 49th parallel would be here, the international border. Washington and southernmost British Columbia is an interesting transition. The orange represents plutonic rocks, the arc plutons, and the blue represents areas where there's a lot more host rock, meta-sedimentary rock, meta-volcanic rock. The other thing you notice, so there's less pluton, looks like the arc is sort of dying out to the south. There's a Cretaceous thrust belt, that's not so important for right now. But there are all these high-angle faults that are going like this, the ones that don't have thrust teeth on them. These are important ones which have Eocene motion, and they're right lateral strike-slip faults. So we're going to focus a little more on the North Cascades now. So here's the boundary. This is a busy map. All I want you to get out of this is that in terms of the range, there are these arc plutons, like the Sierra Nevada. The largest volume, the big flare-up, if you will, is from 96 to 88 million years ago, which overlaps with a lot of the magnetism, the big pulse of Cretaceous magnetism in the Sierra Nevada as well. So these plutons, going from here to here, there's a bunch of them if you look, are in that range. But there are also plutons that are quite volumetrically abundant, from about 78 all the way down to 60. And there are Eocene plutons, but they're all up in this region here. The other thing to focus on, again, are these high-angle faults that cut across things. And one of the things we published on a number of years ago was that we can look at least at the Cretaceous part of it and construct a crustal section. That is, take rocks that at about the same age, formed shallow crust and in deep crust that have been tilted up. Much as in 100 million years ago in the Sierra Nevada, we can go from rocks in the southern Sierras that maybe were at depths of 35 kilometers and then go up to near Mammoth, and they're the same age. At the same age, there are volcanic rocks that were forming on the Earth's surface. So we constructed something similar. Here's the crustal section. Well, one of the things I think that's pretty noteworthy is there are rocks that go down to 10, 11 kilobars, so about 35 kilometers depth in this arc. But again, there's a lot of metasedimentary and metavolcanic rocks. Don't worry about much of this. But the important thing is the rock types are oceanic, so they're amphibolites and metabasalts, metacherts. There are metaclastic rocks. But you can see there's a good volume of these kinds of rocks at quite significant depths. All right, so we think that the crust was based on a number of lines of evidence, partly just the fact that the deepest rocks going down to 40 kilometers, there's still a lot of sediment, metasediment of course, but in most models of continental crust and arc crust, you expect increasing percentage of plutonic rocks and for those rocks to be more mafic. And these are still dominantly tonalites, which are kind of intermediate composition. Okay, so that's a take-home point. And then with the metrology, the estimates from melting, and won't go into garnet signatures and all that, but there's a pretty good evidence that the crust, we think, was at least 55 kilometers, if not significantly thicker. All right, so now we have this thick arc. Now let's look at, again, apologize for changing colors, but this is now something we're going to focus on the Eocene. So here's the North Cascades again. What I'd like to point out to you in terms of the Eocene Plutons, here they are. There are also Eocene volcanic rocks here in red. There are some small bodies out to the west of the same age that are things that have cordierite-bearing granites, garnet-bearing granites. Those of you who had petrology, if you learned cordierite, you probably thought of it more in terms of metamorphism, garnet, etc. But these seem to be forming part incorporation of sedimentary material out in the forearc. So like again, I talked about this sort of anomalous magnetism. That would fall in there. There are sedimentary basins forming in the Eocene. And if we look at these are cooling ages. So if you haven't learned much about cooling ages, the main thing is they tell you roughly, in this case, say biotite, around when the rocks cool below 300 degrees Celsius. So if you look at this, you can see this area down here looks like it's old. It was old and cold and pretty dead by the Eocene. Whereas there's a region in here and in here where the crust stayed hot until about 50 million years ago, or even down to 45 million. So we have a different history, at least younger history, in these regions. I'm going to focus on those as well. And then here's that Siletzia, that large igneous province out here to the west, and probably in the subsurface coming down here. Now, one of the things we have to do is restore this strike-slip fault. It's reasonably well known to have probably about 130, 150 kilometers. And what that does is it just brings some of these sedimentary basins into continuity that I'll talk about a little bit later. But again, trying to restore what we have here. So just some major questions. If you accept the variety of lines of evidence that suggest we have this ridge subduction or the slab breaking off as the oceanic, as the ridge comes in, what was the response? And if we have different crustal levels, how are they linked? I mean, what was happening in the shallow crust and in the deep crust at the same time? And there's an anomalous folding event, and one of the things we learn about, of course, are continental collisions early on with the Himalayas, but what about when you have a situation like Iceland coming in on a ridge, and colliding. What are the effects of that? All right, so let's focus in on those rocks that have the young cooling history that get down to 50. The best represented one is the Skagit Gneiss Complex that I've done a lot of work on in the last 10 years or so. And there's a lot of high-quality uranium-lead ages that are summarized here. Don't worry about them, but the important point is they're pretty young. There's a lot of these are plutons that have been deformed that go from, a lot of them are 60 or 50, so they're much younger than these big 90 million year plutons. And some of them, even though they're all metamorphos, are the same age or more or less the same age as plutons that are totally undeformed and shallow crustal. So we'll just look at this Skagit gneiss. It's a really pretty unit in a minute. Again, orthogneisses, if you're not familiar with that term, that just means metamorphose plutons. So these are rocks that intruded over this time range, but again, only a few of the older ones that have been metamorphosed. So you can think of them as metamorphic rocks, but they're really plutonic. There are migmatites, that is rocks that underwent partial melting, that go down all the way to 47 million years. Rapid cooling. And all this was happening at the same time. We have some plutons that were intruded at shallower levels and aren't deformed. So we're seeing a record of how the mid-crust was behaving. All right, so just some pretty pictures. This is what what some of these orthogneisses look like that have gotten partially melted and injected. So it's my colleague Stacia Gordon there, UNR. There are also areas where there's metamorphosed, where the mica schist, garnet mica schist, which have partially melted. So these light-colored layers would be in the migmatite, would be the partial melt material. You can see perhaps the schist here and as well. So again, very nicely exposed. And if we look at these rocks, so they underwent melting as young as 50 million, sort of protracted history of partial melting. If we look at them structurally, you know, they have foliations that don't do anything particularly exciting. They're more or less parallel to the stripe, just like you'd expect of the overall contacts. But there are folds, and I wanted just to point that out. So if we look at this, these are folds, some of which involve these deformed plutons that intruded as young as 50 million years ago. So we are getting quite young folding in here as well, structurally. And that's something I'll come back to later. Another thing that may come in, I'm not sure how much you learn or worry about stretching lineations, but the rocks, these little white arrows are lineations. I'll focus in on the Skagit gneiss complex and on these rocks I'll talk about in a minute that are also have the young cooling ages. But you notice that the lineations are more or less, you know, they're not parallel, but they're kind of sub-parallel the overall trend of the contacts. Okay. Whereas we'll see in metamorphic core complexes to the east, they're more or less perpendicular to the contacts. So that may become important in a minute. So here are these folds. In the orthogneisses, they're not as spectacular, but these are folds involving some of the migmatite partial melts. But they're upright folds. They're not isoclinal, but they're quite widespread. And they open to tight generally with steep axial planes. And again, these are developed in rocks as young as 50 million years ago. And then the latest ductile strain involves granites, granite dikes or sheets that cut across. So here's some banded rocks, gneisses. These are cut by a dike, but these dikes have a strong lineation as well, so they've been stretched. But that's the last gasp of ductile deformation. And that, before we go to that more north-south trend of the modern Cascadian. All right, now a question that comes up from metamorphic petrology that has been known for the Skagit and also for the Swakanites for a while is that these rocks these rocks were exhumed very rapidly. So we use the term exhumation, means they were just brought closer to the Earth's surface. Not necessarily exactly the same as uplift, but you can think of it maybe in a crude sense, in a related sense. But the idea is these rocks went from being at 10 kilobars to less than 4 kilobars without hardly cooling at all. To do that, that means the rocks presumably were popping back to the surface pretty quickly. And we have evidence from geochronology that that was the case as well. So these things, they stayed hot for a long time, they underwent partial melting, and then they kind of popped back up towards the Earth's surface. Again, all about the same time in this transition period. So the question is exhumation. How? How did you unbury these? Through the grave digging or robbing or whatever. These metamorphic rocks. What happened? All right, so one of the key elements may be this strike-slip faulting. Again, these strike-slip faults I mentioned were Eocene. There's one in particular, a big one called the Ross Lake fault system. There's a whole series of these faults in here. And we can take a look at this. So here, again, this would be our Skagit gneiss over here. Don't worry about all the rock units. But one of the things you may notice is that the boundary of this Skagit gneiss comes up. It's there's a part strike-slip fault over here, there's strike-slip faults here. And notice that everything steps over, so the fault zone comes over here. So in terms of something like the San Andreas system, in a dextral, right lateral strike system, we might think of this as a pull-apart basin if we were looking at modern sedimentary basin. So what this does is it leads to extension, and pull-aparts and strike-slips faults can lead to rapid subsidence, or in this case, we would argue rapid exhumation. Again, just a pretty picture, just to illustrate this flat line step over where the fault goes over. These are rocks that we have metamorphic pressures from around the corner that are about 10 kilobars, so 35 kilometers paleo depth. And then the rocks above are have more on the order of 3 to 4 kilobars. So there's about 15 to 20 kilometers of missing crust between these rocks and the top of that ridge. Okay, so if you've learned this story, if you've learned much about metamorphic core complexes in the Great Basin, the Great Basin, the classic ones, this is a very similar story in the sense of rocks popping up quickly, the crust being extended. The difference is we're in an arc, or what was an arc, and with more of a strike-slip component to it. Okay. So I'll try and move a little quicker here, or not get as much detail. So let's look at the Swakan gneiss next. It's the other unit that has the Eocene. It's actually the structurally deepest part of the North Cascades that we see. It's brought up in the core of an aniform. And these rocks do get up to 12 kilobars. And they're structurally, we can see the contacts. These are the deepest rocks we see. There's a whole cool story in them about how they were thrust or shoved underneath the arc, or deep levels of the arc. Maybe you've heard of the Rand, Kelowna, Oricopia schist in Southern California. I just had a paper in Geology last month comparing those rocks and what the implications are for the similarities. But it's the same story. The deepest rocks look like they're metasediments that were shoved underneath the arc, or at least deep within it. And so let's take a quick look at these rocks. So again, metamorphosed to high pressure. They were rapidly exhumed. Remember, they were part of that, the other one on that pressure temperature plot. And they have a very strong non-coaxial shear. That is, they've undergone a component of simple shear that is associated with a subhorizontal structure, and it gives top to the north shear. So again, it's not, remember I mentioned core complexes, the extension in these shear zones, the classic ones in the Great Basin, are perpendicular or normal to the boundaries of the complex. Here we're looking at things that are going more subparallel. So here's just what the rocks look like. They're actually kind of boring, just unless you like just biotite, feldspar, quartz schist, or gneisses. But they do have some leucogranites in them, partial melts probably, that have some nice little tails. You can get kinematics, but it's a very abrupt contact where and it looks almost depositional, but you go from these rocks that have essentially no arc plutons in them, and they have pervasive simple shear, and then right above them are metacherts and metabasalts that don't have any of that. And there's a pressure difference here, not dramatic, but maybe 2-3 kilobars, which again corresponds to 6 to 10 kilometers. All right, now let's get up to our 50 to 45 plutons a little bit. Important point is there's a lull, and after 60 million year arc plutons, and for many, many years, all of us considered this arc magnetism. But we're rethinking this because there's a lot of changes happen with these youngest plutons before the modern Cascadia, if you will. That is granodiorites dominant as opposed to tonalite. You get a lot of mafic rocks. They're alkaline granites. They're Rapakivi granites, if you've ever seen them. And the neodymium, don't worry about, won't need to worry about isotopes. But the point is, they're much more complicated than the earlier ones. And there seems to be, again, this transition to strike-slip faulting and a component of extension when these came in. And so the question then is, how do these relate to the earlier things? But these dots represent the orthogneisses that I talked about that are 50 to 45, and these would be the plutons. All right, so there's a big change happens there. Here's one, the Rapakivi bearing one. It's called the Golden Horn batholith, which was constructed extremely rapidly. Now let's pull in the basins for the sedimentary component. So there are two basins. There's an older unit called the Swak Chuckanut. There are tuffs in it that have zircon ages, TIMS, real high precision, of about 51.3. But there are some older tuffs, one older tuff out here that's about 57. So this basin seems to have initiated a little bit before the exhumation of this part of the mountain range. It's the oldest of the sedimentary basins. Now, the other basin that's intriguing is called the Chumpstick Basin. And it is bounded by strike-slip faults. And it has all the hallmarks in terms of the sedimentology of a strike-slip basin. Maybe you learn about the Ridge Basin or something like that in California, which is probably the type 1 of the Earth. It has similar rapid deposition. There's real high precision dates on the tuffs, etc. So we just look at the stratigraphy here, a bunch of names, but there's a couple of important points. One is this older Swak Chuckanut Basin has a folding event and an angular unconformity, and then there are a bunch of basalts called the Tianaway basalts that come in at 49.3 million. The basin, this younger basin that I said was a strike-slip basin that's reminiscent in many ways of the Southern California one, the tuff very close to the base is about 49.1. So it looks like you have this folding event and then very rapid deposition, subsidence and deposition in a strike-slip basin. Also basaltic volcanism going on, 2,500 meters of it. So all of this seems to be happening, again, all at about the same time. You know, as everything's been kind of coming in this 50 to 48, 45 million. So that's the important thing from that. And the other is in this area, so here's, again, the colors have changed, my apologies. But this is the older basin that has the blue are fold axes, and then this is the younger strike slip basin. But look at, we also have this incredible dike swarm comes in at about 40. So we start ripping apart, we take this basin, the older basin, it's folded, and then it seems that in unconformity forms, and it seems to be getting ripped apart with all kinds of dikes coming in. At the same time, the sedimentary basin is rapidly subsiding, presumably, and accumulating sediments. So here's what some of these sediments look like for the sedimentary folks. Conglomerates, some nice non-marine sediments, fluvial mostly. If we look at the structures from my students' theses, you can just see the beds defined, the poles to beds define a nice girdle overall with a fold axis that's oriented here. So we have this folding on a regional scale, and then all of this gets intruded by dikes. Okay, so it's not just this one dike swarm, but from 49.3 to about 45 million years, there are incredible numbers of dikes which intrude this range. I think my students and I measured, 1,200 or something like that. So, reason why dikes are useful. So here's it's called a Golden dike. Golden Pluton is thought to be related to, which you can see has kind of a gold look, how it got its name. The reason that structural geologists like to study dikes is because they can tell us something about the regional strain, at least presumably the extension direction, that the dikes will intrude normal to that. And if you want to get into stress, perhaps normal to sigma 3 in a simple-minded look. Others, you could also argue that certainly some dikes are controlled by magmatic centers. Classic would be radial dike swarm coming from a volcano. Or it might be host rock, something it's intruding. Maybe it's intruding joints. It's easier to intrude a joint than to form in exactly the right orientation for the stress field. Or faults, or foliation. All right, so obviously we hope that our goal was to look at these to see if they define that. And again, now we ought to think in strike slip faults. So this is from, I think this is from Fawson's textbook. I'm not sure which structure book you use. But any structure book would have a similar thing. And that is, we can make predictions in a strike slip field, dominated field, what the dikes should be. So if we have northwest striking dikes, then we'll have to tilt this on end. But we ought to have, for something that's striking 320 in a real simple strike slip type model, old style wrench model, we'd have things that would be trending like north 5 east or 005, something like that, whatever you want to say. Folds perpendicular to that. So anyway, let's just take a quick look at the dikes and the orientation. So these Tianoid dikes, this is the Pacific Northwest, so these are big trees. These are probably 40 meters high, Douglas fir. If you can see the kind of brick weathering and then white, the white are the sandstones, the brick red are dikes. So this field of view is probably 50% dike. And so this crust is really being pulled apart, ripped apart, and injected. And so here from my students again, old diagrams, but we have a lot more data. But what you can see from these Rose diagrams and or StereoNet would be that the trends overall are north-northeast. They're well developed through here, and another student subsequently worked over here, and get similar results. So they're interesting in that if you, again, I'm going to keep drawing that analogy with core complexes, but in core complexes, if you have east-west extension, let's say, like the ones in Nevada, or if you like the ones around Tucson or Phoenix, whatever your favorite core complex, those would be more or less perpendicular to the strike of the belt, whereas these would give you extension, or I should say the extension direction would be. These are giving extension that is subparallel to a little oblique to the mountain belt, not the expected orientation. Here's just another one of these to show how some of these can be traced for several kilometers. This is farther east along the Columbia where it's drier. All right, and so again, just to emphasize, we have these strike slip faults, we have these dike swarms. The orientations are not always simple. There's a small one here where the dikes are almost, very high angles. But overall, we have probably, the dominant ones are these north to northeast trending, north-northeast to northeast striking ones. And some are compatible with dextral strike slip, but not all by any means. Okay, so, and we have some really high precision age data on these now from Mike Eddy, who was, when he was at MIT doing, see the uncertainties. Some of these are 30-some thousand years. But when you look at these go from 49.3 down to about 45 million years. So this again seems to be the period where we're really extending the crust. And there are those, some west and northwest striking. Did the strain field change? We're still working on that. There are some that seem to be controlled by foliation orientation in the metamorphic rocks. Another way you could do it, like has happened in the transverse ranges in Southern California, you could get vertical axis rotation, like around a top. That's been well documented in the transverse ranges. But there's no obvious other independent lines of evidence would suggest that's not happening. We don't see any evidence of the magmatic centers. So again, we've got something on the strain direction. And then finally, trying to put this together, we have a complex story of what was all happening. Because remember, I keep saying everything seems to be happening right around 50 to 45. And if we look, we have strike slip faults. So these are going northwest. There is stretching in the metamorphic rocks, in the deeper crust, that's more or less northwest to more north-south. There are dikes, and again, I'm simplifying, that would give extension more like this. And there's, sedimentary basins forming as well. So there's a component of dip slip, of normal slip, of extension. So we're seeing response, whatever is driving it, and obviously I've argued it was the ridge trench interaction, at varying levels. But one of the things that's really intriguing from a structural point of view, it looks like the deeper crust was flowing or extending differently than the upper crust. So there was something we could call decoupling going on, right? Because from the dikes and the strike slip, for the dikes we would get more like this, but we're getting, in the deeper crust, the evidence we're getting from the stretching is that it's more parallel to the origin, or even slightly oblique in the other sense. Okay, so I'll come back, well, I'm almost done, but very end to think about this. But let's look at this from the deeper level rocks. So one of the things that seems different about the North Cascades, going from southern British Columbia into Washington, is if we look at these core complexes that I've mentioned. So here's the big one, the shoe swab, which is the really, really big one. And these red arrows indicate the direction of extension in the ductile crust from well-documented lineations, lots of study. So there's an interesting thing happens, though. If you look in going from the southern end of the shoe swab complex, there are different names in Washington, essentially the same belt. It's pretty much east-west here, But as it gets over to what's called the Okanagan, or Okanagan in Canada, it becomes more northwest, and then really becomes northwest overall in the North Cascades. And so a simple way of thinking that is that we're just seeing, we are seeing the influence of strike-slip on the extension, that it may be similar processes. We're collapsing, extending these core complexes, but at the same time, we're doing somewhat similar in the Cascades, but because strike-slip's occurring, we're getting a greater influence of that, and so the strike-slip component is giving us more extension parallel to the continental margin, or stretching, I should say. Now that still doesn't explain why the decoupling, and that's sort of the puzzle to me, is the brittle deformation. If you remember, those dikes were probably oriented 0, the average is about 0.20. So that would be like this. So 90 degrees to 0.20 would be giving us, something that would be more like 290, 110. So the brittle crust is not extending all that differently than the ductile crust to the east. Do you follow that? That seems counterintuitive. And the only argument, I don't think how this exactly works in detail, but one of the interesting things down here is we're at the very southern end of a big super terrain, of what's been called Rangelia, the original terrain. And there's this big Cretaceous thrust belt that I mentioned. And that thrust belt seems to end right at the southern end of the North Cascades. So one argument could be that we're getting differential flow along the strike between thicker crust and where you have really thick crust and thinner crust, and you're getting flow from the thicker crust towards the thinner. That's been documented actually like in the Ruby Range in Nevada, where you get something similar. So that could be driving, if the crust is really weak, I think that happens in the Andes as well, beneath the real thick crust in the Altiplano and Puna, Argentina, Bolivia, is that you have a lot of crust here and it gets thinner, you're going to get flow not like thick and cheese from the thick to the less thick. All right, well, that's still pretty speculative. Finally, just again to bring it all back to what I initially started with the collision, just want to point out again that we have this oceanic plateau, perhaps, this Icelandic type thing on a ridge or near a ridge, coming in. At the same time, we're getting the core complexes, we're getting that, all that, and we would interpret, or we have interpreted, these folds, and remember that there was that folding event that caused the upright folds in the metamorphic rocks. It folded those Eocene sedimentary rocks, the older basin, and when we straighten out the continental margin, before it got messed up by basin and range extension, you can see that we have this Siletzia coming in, and there are fold and thrust belt down near Roseburg, Oregon, and southwestern Oregon. It's slightly older, but very similar in age to the folds we have in the Squawk, and then in southern Vancouver Island, and then the folds in the deeper crust as well. So we think this is a manifestation of the collision. And again, it's just like any collision. It probably was it's not always exactly synchronous, probably a couple million years older in southern Oregon. But the same collision. And then again, coming back to this diagram, the big take-home is that this collides. We have a reordering. This ridge comes in, and we start getting this major strike-slip component, and that is when the strike-slip faults either initiate or they accelerate in motion, and we start pulling apart the crust to get the sedimentary basin forming. The crust is getting ripped apart in a way to get these dikes to come in the shallow crust. And then in the deeper crust, there is exhumation. It's getting extended, or in the strike-slip being exhumed, and there's crustal flow as well. And so all of this big change happens, again, around 50 to 49 million. This continues for a few million years, and again, here's just another diagram showing how you'd have this thickened crust coming in. And the final thing is that as this all happens, afterwards you're going to have a reorganization and a new subduction zone, or at least the slab breaks off, the founders, and we form the modern, if you want to call it Cascadia or not, the modern subduction system. Because at 45 million, if you recall, I had those dikes that have that strong subhorizontal lineation, the exhumation, all of this sort of 45 is the big end for all these things. And then there's a few million year gap in Washington, or at least northern Washington, and then volcanic rocks volcanism starts up again, some plutons, and these are in a north-south trend, and the same thing happens all the way down to like around Wairika in the Cascades, east of Wairika. You can trace all the way up through Oregon to Washington. It's all happening a little different time-wise by maybe 1 million or 2 million years, but we've essentially formed the modern north-south subduction zone and north-south arc. And that presumably all, again, results from this Siletzia coming in, everything getting folding, the formation of the strike slip faults, and then a new subduction zone or the subduction zone jumps out. Whatever way you want to think of it, we start initiating the new subduction system, which explains, again, why we go from these northwest trends, all this cool stuff happening if you're a structural geologist, tectonicist, to then the north-south arc, which is cool as a volcanologist if you're an igneous person, but less stuff going on in general. Okay, so I think I've pretty much given you all that. But again, a lot of different things happening. We can look at them at a lot of different crustal levels. Cool. Thank you.
Let's go for a few questions.
Question. Along any of these transpressional zones, do you see melanges?
No, the melanges would be, it's actually interesting whether the melanges are actually beneath the whole thing. There's something called the Western Melange Belt that is out in kind of god-awful country to do geology, northeast of Seattle, and that in the lowlands, it's all covered by forest. But there are melanges, and some of the, we've learned that some of that's getting up to about 72 million. So it may actually be the material equivalent to some of that Swalcan gneiss I mentioned, which was buried to 12 kilobars. They're similar detrital zircon populations. But there may have been melange, in fact. You're familiar with the Bridge River, Cache Creek stuff that Jim Monger and many others worked on in British Columbia. We've correlated some of the rocks in the Cascades, but they've undergone amphibole facies, metamorphism, and extreme ductile deformation. So any of that sort of structure has been wiped out by the strong ductile deformations.
Yeah. So we've got a lot to unpack. So there's a lot going on. I'm trying to wonder, you kind of threw out a number of 2,500 meters of basalt that came in at around this time. And
so that would be presumably when the transtension, that would be right after the collision, and the transtension initiates.
Yeah.
So volcanism is occurring at the same time the subsidence is occurring.
Okay. So I'm wondering, as with a lot of bleeding edge ridge coming in to a subduction zone, you get really unusual geochemical signatures in volcanics.
Yeah.
Does that show up in these basalts, or are they typical mid-ocean ridge?
They're not. They are bimodal in the sense there's about 10% rhyolite, So, and there is an island arc signature, but that, at least petrologist colleagues argue that that may be because of what the mantle that's melting actually has a subduction signature. The stuff that's more anomalous is to the west, that's about the same age. That's where there are Eotites, and about the same age as these cordierite-bearing granites.
Any ophiolites that pop up through this ridge collision?
There's some stuff out near, I don't know if you know Seattle very, very well. There's some stuff in the islands right across from Seattle, a place called Bremerton. But anyway, sort of on the edge of the Olympic Peninsula, which again is rainforest. And there are some things that there are some gabbros and basalts, and that have been called, that may be equivalent to an ophiolite. And there is some stuff on Vancouver Island as well that it's been argued that, but not a good ophiolite with sediment. So,
massive sulfides, anything that you'd find with big
No.
old hot smokers?
No.
Trying to look for exciting things you would find in
No.
mid-ocean ridge.
No, the mid-ocean ridge, and that may be because this stuff really didn't, you know, mostly what you see accreted, there is in this crescent Siletzia. The old story, and it's not as simple, was that there was morb, there were definitely pillow lavas in the older part of it, morb type rocks, with island art, or with, excuse me, within plate basalt chemistry, Ocean Island on top, which made a nice story like Hawaii with building, and it's not that simple. That always was the story, that we had the hotspot magnetism on top, right on top of the ocean ridge. And that, but no, because that came in, and part of the problem, there's the geophysics, the EarthScope, this big geophysics project, which was carried out across North United States the last 15 years. So one of the big findings is this big subvertical slab of high velocity, which means high density, probably cold, that's actually interpreted to be the slab of Siletzia way in there, but there's no good ophiolite. No.
Yeah. Would the tonalite have been from the earlier subduction?
The tonalite would be presumably the Coast Range earlier subduction, yeah. So everything was very typical of the Coast Range batholith, dominantly tonalite, a little bit of granodiorite, a little bit of diorite gabbro, but kind of classic arc. And it goes to 60. Like I said, we always just thought that the 50 was just the younger part of the arc, but there is this lull at 60, then to 50, and then the magmatism gets so much more diverse, and that's why, tentatively, I would suggest that this is really not arc magnetism anymore, but this is related to that. Now, the folks who work farther north in BC, the timing is exactly the same, but they would argue that farther north in like Cecil Robinson and people like that, I think Cecil would, would argue that some of that is arc related, that is getting pretty young, maybe not quite as young as 50. But the vents aren't exactly the same along the length, not surprisingly, of the coast batholith.
I've never even considered the decoupling of the top and the bottom layers. You said it had something to do with the deeper crustal layers being larger.
Yeah, well, that's kind of...
Can you talk about that for a little bit?
Yeah, I don't know if it's BS or not, but it's speculation. I'm trying to think about how that can come, because why certainly the upper crust and the lower crust could both be deforming, one ductily and one brittly, but usually the extension directions, like I think in the core complexes in the Great Basins with the associated, the Great Basin, core complexes and associated extensional basins, generally the extension you get from the brittle normal faults is the same as you get from the myolines. Mm-hmm. There's an exception when you get in the Ruby Range near Elko. the crust, the deepest levels of the crust actually have at least flow that seems to be at right angles to the upper, to what you see right below the detachment fault. So one possibility is if you have, again, a long strike, not a cross strike, like you typically think of, but a long strike that there's different crustal thicknesses. And with weak crust, you can get flow. So again, this is the range. Rather than getting flow perpendicular to it, or extension like we normally would think, if you have significant difference in crustal thickness, which the argument is that the crustal thickness results from the collision of this Wrangellia terrane, that if that's the case, and at your end of the thrust belt, and you have this big thickening, you could get flow parallel to the belt from thicker crust towards areas of thinner, to even out the crustal thickness. And that's been, like I say, in the Andes, that presumably happens, that's the interpretation at least, from seismic anisotropy, that is happening. You probably know, or you know, the Altiplano and parts of Bolivia, the crust is 70 kilometers thick. And the Altiplano, or the Puna Plateau, which is really hot as well, it's more like 50, 55, but that's still much more, that's much thicker than what our typical textbook models of 30, 35 kilometer crust. And so the idea is you are again sort of evening out, simple, but the gradient in terms of crustal thickness to even it out. And because these rocks are so hot, so pitches that are partially melting, they were weak enough to flow under that kind of a gradient. Then with a brittle crust, not.
Maybe last question? That'd be great.
Okay, one last question. It relates to this last question. Are there any seismic reflection profiles that might suggest a discontinuity?
Now,
There
unfortunately,
used to be something called the Conrad discontinuity.
there's lithoprobe lines in southern British Columbia, and that's the best seismic. Anyway, I'm going into why there aren't the COCORP, which was that old. The roads aren't amenable to going through national parks and that sort of thing. And anyway, there they see the crustal reflectors going down pretty deeply. So there's, you see a boundary, and you see, particularly beneath the core complexes, but no, not a nice simple one.
All right. Well, let's thank Dr. Miller for having us on.